A warm welcome to everyone who has been joining our webinar. It's a pleasure to have you with us today. Within the next 1 to 1.5 hour. My name is Ehsan Qasem Ali, and as you will see soon, I'm one of the moderators for this webinar. Today, our colleagues are going to talk about design of experiments for alloy development. And this is a webinar that is organized within the WebLearn project. It's a project that is supported by Knowledge Foundation in Sweden. As you will hear soon, it's number 27 webinar within this 2-year project that is running right now. And we have different modules in this webinar, in this project that are dealing with different topics related to metal and polymer component manufacturing. And today's webinar is related to module number 7, which is simulation technology in metals and processing. And also I can say it's a collaboration with module number 6, I think, which is about alloy development. So we have a little bit of cross-disciplinary collaboration here. Next slide, please. As I was saying, and some of you heard, we had more than 43 registrants for today's webinar. And as you can somehow see on the list, we have representative from around 19 or 20 countries around the world, from Australia to Africa to US, America, and also Europe. It's a pleasure to have this truly international spectrum of participants with us, and we see it as an honor to host you today. Next slide, please. As I said, WebLearn is a project that is supported by Knowledge Foundation in Jönköping in Sweden, and is run by School of Engineering and Jönköping University. The focus is to run interactive, short and spot-on webinars related to metal and polymer component manufacturing. And within this project that started around 1.5 years ago, or around 2 years ago, we are running bi-weekly webinars. So every 2 weeks, we have one webinar related to the topics that I mentioned. If you're interested to learn more about the project, the website is on the slide, ju.se/weblearn. Next slide, please. These are the moderators for today, myself and my colleague Madeleine, that you see and you heard her also. Next slide, please. It's a pleasure for us to host you. But most importantly, more important than us, are the presenters of the webinar today. Jakob Olofsson is Associate Professor at the Department of Materials Manufacturing, School of Engineering in Jönköping University. And Patrick Conway is also one of our research fellows at the Department of Materials Manufacturing in the School of Engineering. You will hear more details about them soon. The agenda for today you see on the slide. After this short introduction, the presenters of today will present the topic, and hopefully by 11 we will be ready for a panel discussion. As I mentioned, we try to have our webinars more interactive and try to engage participants into the topic by having more discussion about the topic. And we hope to wrap up the webinar within 1.5 hours from now, 11:30 Swedish time. Next slide, please. Some technicalities. We would appreciate if you could turn off your microphone during the meeting. Questions are more than welcome and actually encouraged. You are welcome to raise your question in the chat during the presentation, and we will answer them at the end of the presentation, so at the end of the webinar. As I mentioned, panel discussion is an important part of our webinars where you can give inputs and share ideas. So you're more than welcome to participate and raise your questions, or even participate in the discussion if you have opinion. And our webinars are recorded. You will receive the presentation material as well as a recorded webinar within a few days after the webinar. If you would not want to have your picture in the recording, please turn off your camera. The thing is that we do not record the panel discussion. We only record the presentation. So during the panel discussion, if you would like to, you can turn on your video as well to be more engaged in the discussion. Next slide, please. And for those who don't know Zoom, I think we all know because of the pandemic, we all got expert in Zoom, but just in case, this slide shows you where you can find how to turn off or on your microphone, how to turn off or on your camera. And if you have questions, how to raise the questions in the chat. You can send the questions either to everyone or send it to myself or Madeleine, and we will take care of it. Next slide, please. That was a short presentation from my side, and now I would give the scene to Jakob and Patrick to show us what they have to present about the DOE and alloy development. Exciting topics. Thank you, Patrick. Jakob, please.
Thank you, Ehsan. Thank you, Ehsan and Madeleine, for sharing this session also, and welcome all of you to this webinar. I hope we have an interesting hour and a half in front of us. And I'm very happy today that today I have my colleague, Patrick Conway, who just disappeared out of his camera, but I'm happy to have him on board today. And we're going to talk about design of experiments and some different examples and applications of how to use that in our research. So the agenda today, we will introduce ourselves a bit, then I will say something about what is design of experiments and give an example of how to use DOE and ANOVA, which is another concept I will introduce also here. The example is on understanding and quantifying the effect of microstructure on properties and seeing how we can really evaluate the data with statistical significance. And then Patrick is going to introduce a case study on alloy design before we move on to the panel discussion. So Patrick, feel free to introduce yourself a bit here.
Thank you. Yes, as Jakob said, my name is Patrick Conway. I'm a postdoctoral researcher here at Linköping University in the Department of Materials and Manufacturing. I did my studies, PhD in Sydney, Australia at UNSW, and my research has always been focused around high entropy alloys, composition complex alloys, and the alloy design process behind that. And with so many different elements that we can mix with these HEAs, the design of experiments and ANOVA analysis been very, very valuable. So looking forward to taking you through a bit of a case study of one of our projects we have running here. Yeah, so I hope you find that interesting.
Thank you. And a bit of words about me. I did my Master of Science in Mechanical Design, Mechanical Engineering at Linköping University. Then I worked a bit in the industry with as a design engineer and CAE engineer. So I was working both with geometrical design, but also with the coupling towards manufacturing and production, and also finite element simulations of the stress strain analysis and crash analysis and similar aspects. Then I returned to academia and did my PhD at Jönköping University. I finished in 2014 and have remained here since. And my research interests includes casting simulation and the modeling of solidification, microstructure formation, and mechanical properties in different ways. And especially my focus is on coupling between casting simulation and finite element simulations, both for stress strain and for fatigue predictions. So I will start a bit, and some of you maybe joined the webinar we had some time ago on design of experiments for casting simulations together with Magnus Wirsén. But I'm going to recap a bit of that, kind of an introduction to what is DOE and what are some basic concepts that we encounter when we talk about this. So what is DOE, design of experiments? Well, if you look in Wikipedia, the base of all truth, the design of any task that aims to describe and explain the variation of information under conditions that are hypothesized to reflect the variation. So basically, if we interpret that a bit more loosely, how can we choose to change some variables that we think have an impact on an output? And also how we interpret this variation in the output. So if we have a process that we are interested in understanding and knowing more about, we give it an input and we check the output. Then we change these variables that we think have an impact on the output. So we change that, give it another input, and we see what is the output. And a simple example of that can be the process of understanding how does the freezing temperature of water vary with sugar content. So if you have different amounts of sugar to the water, we start with having pure water, then we measure the temperature, then it's 0 degrees, it's the freezing temperature. We change the sugar content to 50%, well, then we see that the temperature goes down to -5 degrees. So by testing different values here, we can get an understanding of how this process behaves. And more generalized, we have what is called a response. That's the output, in this case, the freezing temperature. And we have our design variables or factors. These are the input variables that we can change and think affects the response. So when it comes to this, we also have what is called a design space, which is the region or range in which the design variables varies. Like what I said before, we have a sugar content that varies from 0 to 50%. So DOE is basically a structured approach to analyzing such processes. Why should we use this? Well, basically, it's a methodology to gain as much useful information as possible. And what do we mean with useful? Well, it should be relevant, but it should also be statistically significant. And we can use it to understand complex processes with many variables and responses. And it helps us handle many design variables and interactions between these variables in a smart way. And you typically talk about 3 main objectives in DOE. You talk about screening, which is when you want to find the most significant design variables. You talk about optimization, when you want to find the point in the design space that gives us the best response value. Or you talk about robustness, which means that you want to find a region in the design space where the response is stable. If you look at the design, a response, which depends on the design variable, you can find a nominal optimal, but in this case, it's a very local point. So maybe it's hard to stay within that, within your production, for example, stay on top of that top. And if you just slightly move off that top, you will drastically change the outcome. Maybe this could be a more robust optimal point, which is more stable in terms of production. So it's more robust. In casting and solidification, we typically have a lot of variables to handle. We have different design variables, geometry, chemical composition, feeders, mold design, etc. that we can change. And that gives us typically some kind of response that we're interested in measuring. Like mechanical properties, porosity, yield, hotspots, or part price, or whatever. You can have many different responses. So taking this a bit further, when you do this, you want to do this in a quantitative way, that you check the numbers that you put into the process and you get it out. And to relate that, you typically use some kind of regression model. So it's a function that describes this relationship between one or more variables and a response. And for screening, you typically use a linear model to understand what is the most important variables. So what we do is we make a simple model where we have a constant value plus a constant times each of the factors that we are investigating. You can also expand this with interaction. For example, if you change x1 here, one of our factors, the effect of x2 might change. So then we have an interaction between those two terms. For optimization and other techniques, you can also use higher order models that where you want to might more find an optimal point, for example. But this is typically what we use to understand what is the most important variables. We use a linear model. Yeah, the interactions here can be quite of interest sometimes. And in the previous webinar, we looked also on how to choose our design points in a smart way. We talked about factorial designs, or either full factorial designs or reduced factorial designs, which can help you pick your design points, that is, choose your variable inputs in a smart way in order to get a lot of useful information out. We could see that if you do a full factorial, try all different possible combinations of factors, then you typically produce a lot of numerical waste, really. So you're just doing a lot of experiments without gaining so much from them. So I would like to walk you through an example of how this can be used. And this example is about understanding the influence of microstructure on a material property. This example is taken from a paper that we published some years ago. It was a collaboration with me and Amir Ghasemali, who was at that time a PhD student here at the Jönköping University. And also together with Anders Jarfors and Ingvar Svensson at the university. So we investigated a compacted graphite iron. That's a material which some of you might know very well. It's one type of the cast irons. We typically talk about gray cast iron with flakes in the graphite precipitating at flakes. CGI, which has a more of a vermicular or compacted graphite shape, or ductile iron, where the graphite precipitates as nodules. So you see the example of the microstructure and the matrix between the black particles here. It can be perlitic, ferritic, or a combination of this, where perlite is typically hard and strong, while ferrite is more soft and ductile. So CGI is an interesting material because it has higher strength than ordinary gray cast iron. It has these flakes, but lower strength than the ductile iron. But also its thermal conductivity is kind of in between these materials. So that's why it's quite interesting to investigate this material. And what we know is that adding silicon, that promotes the formation of ferrite, but it also strengthens the matrix to solution strengthening. So we know that silicon is one of the interesting factors to investigate. But then we also knew that the morphology of the graphite, it also affects the strength. And one measure to look at when you talk about the morphology, so that is the size and shape of the graphite. One such measure is nodularity, which typically is less than 20% for CGI. It should be below 20%. It's calculated like this by this equation. So basically it calculates how many nodules do we find. As in this microstructure, we can see some round parts of the graphite, while some had other shapes. So you use this equation to calculate that based on the area of the nodules, 50% of the intermediates divided by the sum of the area of all the particles, and then multiply by 100 to get it in percentage. Another factor you can measure is nodule count. And you can also measure perlite content to see if we have some perlite in this material. So what we wanted to know here in this example is what is the quantitative influence of variations in silicon and graphite morphology on the yield strength of the material. And not only with that, we also want to know which factors are the most important ones to consider. So should we focus on measuring nodularity or nodule count or perlite content, or what is actually the factors that contributes to the yield strength? So here our variables or factors are the silicon content, nodularity, nodule count, and perlite content. And the response that we're interested in measuring then is the yield strength of this material. So in order to investigate this, we set up an experiment. So we cast this geometry that you see here in the picture to the left. So it's quite a large casting, which contains several different thicknesses. As you can see, there are different plates going out from this geometry with different thicknesses, which means that we have different cooling rates. That means that we should get different microstructures in terms of both ferrite content could vary with the cooling rate, but also the graphite, both the nodule count and the nodularity here can be different in this different cooling rate. It captures quite a wide range of cooling rates. You see the thin sections here are from 3 millimeter, 7, 15, 30, 50, all the way up to 75 millimeters, which is quite thick. So that will take a long time to solidify and get a completely different cooling rate than you have in the thin samples here. So this is all cast in one at the same time in a sand mode. And then this is sectioned, as you can see here, into different parts, A, B, C, D, E, F, G, and from which we can both take tensile specimens and microstructural analysis samples. So we can both check the microstructure and do tensile testing at these different conditions. And then we do this for 3 different levels of silicon to investigate what is the influence of silicon here. So 3 different melts were prepared. So the base melt, you can see the chemical composition here, had a silicon content of 3.6. And then we did some different tests here with different combinations. And what we ended up with was a low silicon, which had 3.66% silicon, medium, which was 4.1 about, and high silicon, which was 4.6. So you can see we changed the content of silicon. Also the carbon content changes a bit, but mainly here it's the silicon content, which is interesting because it gives a strengthening effect. Also, so what do we get? Well, as you can see, this is the microstructure results for different alloys and different thicknesses of the samples here. And this is, you can see this varies a bit. And if you quantify this with a microscopy, we can measure the nodule count and the morphology. We can also see if we find any perlite in here. And if we look at the tensile curves, we can also see that the material behaves quite differently. It gets different strengths. The blue curves here are with the low silicon with different thicknesses. You can see that the thickness also affects the strength here. So the cooling rates has changed the microstructure, and we have also then a different strength of the material. The red curves here shows the medium silicon content, and the black ones, the high silicon. So we can see that there is a clear effect of the silicon content here. If we then take a look at the numerical data, and you can see the factors here, the values for each data point that we have. So we have a lot of samples, and we have the corresponding yield stress. So now we want to have a look at this with just looking at the data, the quantitative data, and trying to understand what is it that we really see here and what can we really say from this data. And the first step, of course, is just to just plot the data, just show it in a graph. So this shows the obtained yield stress at the different silicon content levels. And you can see we have different levels at different silicon contents. And the range seems to be more moving upwards. So there seems to be an increasing effect. Yield stress seems to increase when we increase the silicon content. But there is also something else, because you see there is a scatter, and there is a change, there is a range of values at these different. It's not just that if you know the silicon content, you can exactly say the yield stress. So there must be something more here that changes. So that's why we go to DOE and also start to then doing a linear regression model. So basically what we do is that we do a linear regression to fit a model to this data. And now we use all of these factors to begin with. And we can see that we will end up with a numerical model that looks something like this. So we have, see if I maybe can get a laser pointer here. We have the constant value, which we remember from our linear regression example before. Plus, for each factor here, we have a factor. Now, this is an equation that now relates these factors to our response. But this is, sort of say, purely mathematics. You can fit a really nice model to your data, but is it really significant? Is it relevant? And is it really showing you something that is worth knowing? So what you have to do then is to look at this model and doing what is called an ANOVA, an analysis of the variance, and start looking at this from a more sane statistical approach, or with understanding what is it really that we can tell from this model. So what people typically do is that you look at the R squared, because people have heard that R squared, that's a good measure. It shows the fit between your measurements and the model that you have, calculated as the square of the deviation between the measurement points and the predicted value. The problem with R squared is that is a measure developed for linear models only, and people tend to use that for nonlinear models sometimes in an incorrect way, because R squared itself, it's easy to make it look good. R squared should be equal to 1 if there is a perfect fit, and 0 if the lower, the worse the fit is to our experiments. So we should be close to 1. And you can see here we are at 0.9853, which looks actually, it's very good. It's a very good fit. So this model very well describes fits very well to our experiments. However, one should also be aware of some other things, like I don't going to go into the numerical details, but like the adequate precision. But that is a measure that also is important to look in, if you can say if this is really a relevant measure. This should be above 4, and in this case, it looks good. So far, this model looks like it's quite good. However, we also do look at some other data in our analysis of variance, ANOVA. We have to say, now we have determined a lot of factors, numerical factors, 1, 2, 3, 4, 5 different values out of this data. Do we really have enough data to say that this value is exactly, let's take the nodularity, for example, 0.83. Are we really sure on that? How sure are we on knowing this factor? Well, then we have to look at the ANOVA table and look at, especially I will turn my attention to the p-value, which tell us, is this a statistically significant value, or is it just related to noise? We have noise in our measurements. We have variations in our measurements. And then we see that this model, okay, the model itself can be considered significant. And the factor for the silicon content, yeah, that is also statistically significant. We can be quite sure that this is, we of course, we have a variation around this value, but we are quite sure that this is okay. The nodularity, this is quite a high value. It should be less than 0.0001. That will mean that we have a very low risk of having the incorrect value. But here we have actually 11% chance of having an incorrect value here. And if you look at the nodule count, it's actually not so good. We have 50% chance of this value being the right one. So maybe not a very good model. Also, to look at the effect of the different factors, see which one is most important, then we cannot really tell from this equation on the top, because this silicon content, it goes from 3.6 to 4.6 about. The nodularity, it varies more, and the nodule count also has different values, which is typically in hundreds. So this term is hard to say anything about. So we need to look, in order to say the relative influence of the different factors, we need to look at the equation in terms of coded factors, which means that we are normalizing the values from -1, which is the lowest value, to +1, which is the highest value. And here we can see different values here. Let's see if I can again get the pointer here. For A, which is now the silicon content, we see we have a high value, 127.11. So that means that it has a very high impact on our results. And then we can compare that to C and D, which is our nodule count and perlite content, which is around 8. So this is 15 times lower than the silicon content. So in this range that we're investigating, the silicon content is by far the most contributing factor. So silicon is the highest effect here. Then we can see it for B, nodularity. Yeah, that also has an impact. But nodule count and perlite content, based on our data, it's not, they don't contribute very much to the yield strength model here. So the conclusion, well, the model itself has a good fit, but and the silicon content and nodularity have the highest influence. And we can see that the model is statistically significant, but the factors are not established with statistical significance. So there is a small contribution from nodule count and perlite, but we cannot really establish them either. So one thing one can do, and typically people do, is to increase the number of terms in your model. And you add the interactions, and what happens then? So here you see our model becomes really long and complex. We have the silicon content, and we have silicon content times nodularity and times nodule count. And we can do that. Mathematically, we can fit a model with this. But is it really relevant? Well, let's look at the fit statistics again. The R-squared value, well, it's almost the same. So we have added a lot of terms, but we don't really get a better fit. The adequate precision has gone down, so it's not really better. And looking at the significance of the terms, we can see, okay, silicon content, that factor is still significant. But every other factor, now we are trying to extract more knowledge than we have in our data, because it's so much. Now we are really having trouble estimating all of these factors, because we don't have enough data to do that, draw that conclusions about them. So conclusion from adding this, the fit is the same, and still the model is statistically significant, but the factors, there's no way we can establish them with significance. We're not sure of them at all. So the conclusion we can see is increasing the order of the model, that does not increase accuracy, and we are now not more statistically relevant than we were before. So instead of increasing the numbers of factors, we should really try to decrease the number of factors. So what we make is a reduced linear regression model. So we exclude some of these factors. So we could see that silicon content and nodularity was the two most important factors. So if we instead make a model with just these two factors, well, then we get a model that looks like this. What does the statistics tell us about this one? Well, okay, let's look at the R2. Well, it's still the same as when we started, more or less, 0.98. And we have increased the adequate precision even more. So it's actually fits very well. And we still see, okay, both these factors are highly significant when we look in the terms when on the coded factors. So we have only significant terms now. And looking at the statistical significance, they are all now significant. So this is actually the knowledge that we really can make from this data set that we have with statistical significance and being sure of that what we say is correct. And this model is actually working very well. It fits very well. So the conclusions we can make is that it's by only including silicon and modularity, we yield a regression model that fits as well as including all factors. You can see the R² value in 0.98 and 0.98. It's just a slight very difference on the third digit, which is really small. And now we have a model which is statistically significant, and the factors are established with statistical significance. So now we know that that these factors that we have are okay. I can see we have a question in the chat. If I'm going to demonstrate how do you reduce the factors. So basically what I do is just that I do a linear regression model, a linear regression just using these two factors, silicon and nodularity. When you do a linear regression, you have to choose what are my variables that I want to fit to this. So in this case, I just chose these two instead of all the four that we had. So looking at how this model compares to the experimental data, this plot to the left shows the predicted value on the y-axis and the actual value on the x-axis. So in a perfect world, if our model was perfect, it should be, these dots should all be exactly on the line. But you can see we are very well describing this, these points. They all follow on this line. We always have they have a slight deviation around this line, but they all follow the same trend. If we would have an incorrect model or missing some important relevant term, we would have outliers lying further away from this line. To the right, we can then also plot this as a surface, so we can see visually what happens now if we change the silicon content. Well, you can see we're going quite steeply upwards in yield strength by increasing the silicon content. And if we have different nodularities due to different cooling rates, you can see by increasing the nodularity here also increases the strength, which is also makes sense based on what we thought in the beginning would happen, that silicon content, well, it should strengthen the matrix, and it does. And nodularity, well, we know that completely nodular ductile iron is have a higher strength. So increasing the nodularity should increase the strength. But what we have done now is that to really quantify this and see what is the effect of the variables, which are the most important ones, and we can see how large the effects of this is. Again, we have a question in the chat. How can one decide which factor should be included in the optimized model? Yeah, that's a very good question. And typically it goes like this, as I showed you, that you start with including the ones that you have measured. You try to start from that, as much use as many factors as possible, and you kind of see that okay, well, this factor is not really contributing, and then we can try different ways. Now there are different approaches to doing this, and you can also work with more advanced methods to fit your data, but we're not going to go into that in more detail today. Basically, you can say that machine learning and other things that people tend to talk about, that's basically the same thing, just doing it in a smart way and letting computers doing it for you in a smart way. But basically what you want to do is to understand what is the coupling between my input and my response. Okay, with that, I'm done with this example, and I would like to hand over to Patrick for our next part of this webinar.
Thank you, Jakob. Very nice. Did you want to wait a moment to see if there are any questions from your part?
Yeah, you can request control in a way.
Okay. Doesn't seem like we have any questions. So I think I'll jump into it and we can take all the questions at the end. I'm going to talk a little bit about a case study in alloy design where we have applied design of experiments and a bit of ANOVA analysis. So I'm going to very, very quickly cover high entry alloys as quickly as I can, and then move into the actual specific project we have in designing lightweight alloys, and more specifically, the results and the ANOVA analysis from these aluminium silicon alloys that we have produced. So in case you don't know, high entry alloys are a fairly new design strategy for alloy design, and it was first introduced in 2004. And it basically, instead of looking at the corners of phase diagrams, we move away from the corners and we move towards the center. And by increasing, in theory, increasing entropy, we can decrease the Gibbs free energy, which is going to give us stability of our phases. This allows us to create, hopefully, a single solid solution phase in regions where typically we would have thought beforehand that we would have produced a lot of intermetallic phases. And this can give us some very interesting properties by mixing a huge different range of atoms, different sizes, different electron configurations. We put a lot more strains and stresses on the lattice, and we get some very interesting properties. We can also mix these atoms in different configurations so that we have complete random ordering, or we can have multiple phases with some form of short range or long range ordering. All of these, I guess, mixes of different atoms can give us some very nice properties. And there's been quite a few studies into some of the more fundamental high entropy alloys, which have shown we are really breaking away from the traditional strength versus ductility trade-off. And we can start producing some alloys with pretty exceptional strength and ductility. So what we wanted to do was take these high entropy alloys and apply it to some more conventional alloys that are needed to be, I guess, improved within the industry. And we've taken this to a project that we are still currently running called Novella 2, funded by the Knowledge Foundation, same one for the WebLearn project. And this question came from our partners at GKN. They are currently using a high performance aluminium alloy, and they needed a little bit more thermal stability. They wanted to run it a little bit higher than sort of the 150, 160 degrees Celsius that the aluminium cast alloy can run at. But the next step up was titanium alloys. This is obviously a lot more expensive, a fair bit heavier as well compared to aluminium, and sort of over-engineered for what they need for their purpose. So what we wanted to do with this project was to try to fill this gap, density and property gap between aluminium and titanium. We decided to come at this from 3 approaches. One from the aluminium side and see if we can increase a bit of the solid solution hardening. We can increase the density to try to increase the strength. We also came from the other side, from the titanium-based side, using Ti64 as a reference alloy, try to make it a little bit lighter, try to reduce the cost, and then also a fundamental HEA, composition complex alloy approach, just looking at thermodynamics and what will work fundamentally. What I'm going to look at today, dive a little bit deeper, is into some of the alloys we have produced from this aluminium-based approach. What we first needed to do was to screen the periodic table to see what elements we can actually squeeze into an aluminium silicon cast alloy without forming unwanted phases. And from literature, we picked a bunch of elements. We performed some high throughput screening. I don't quite have time to go into too much detail of that, but we found we had a few elements which had decent solubility within aluminium silicon without producing any unwanted phases. From this, we actually picked 4 of the elements: magnesium, silver, copper, and zinc, to produce a variety of different alloys. We didn't use gallium because of the low melting point, and we're trying to increase thermal stability. So what we did is we designed a bunch of alloys within the solid solubility of aluminium and silicon from these elements of interest. These are the compositions we came up with, and you can see we have varied the copper, magnesium, zinc, and silver in different steps. This was with aid of both design of experiments and also thermocalc to show where our solubility limits are for each element in combination with each other. We cast alloys here, and then we did a standard T6 aluminium heat treatment. So we first solution treated the alloys at 500 degrees for 8 hours to try to make sure we don't have any unwanted secondary phases. And what we found was all the microstructures were pretty similar to each other. We didn't have any extra phases in any of them. We did see a few very small ion intermetallics across the board, across all alloys. And this is a side effect of impurities within aluminium castings. But this gave us a really good base to then investigate a wide range of different properties and try to identify what effect the different elements have on these properties. First up was the tensile properties of these alloys. And you can see we have a nice range of yield strength varying from about the 150 all the way up to close to 250. And then we have quite a big trade-off in maximum elongation as well. We also have studied the hardness of these alloys and calculated the solid solution hardening effect from the combination of all the elements. And then we want to try to identify what effect the factors, our input variables, in this case, our compositions of the different elements, have on all of our different properties that we are interested in. For reference, we are sort of most interested in hardness, yield strength, and elongation, because if we can get a nice balance between those properties, we're going to have a nice alloy that's both formable, processable, but also strong enough and useful at the applications that our partners need it. Looking at the outright, properties, just plotting them against each other, you can see, as we sort of expect, we have a decent correlation between the elongation on the x-axis in the middle here and the yield strength. And ideally, we want to be pushing as much as we can towards the right-hand side of this plot. Of course, we always want to be getting higher yield strength without decreasing the formability. So we want to be trying to identify what elements and what factors are potentially helping us with increasing elongation and increasing yield strength. Across some of the other graphs you can see here, the hardness was quite closely correlated to our calculated value of solid solution hardening, which is always a good sign. And the hardness was also a fairly good relationship with the yield strength. But as Jakob was discussing before, we want to actually look into the ANOVA analysis for these alloys so that we can actually understand the significance of each element and the significance of our model when we're looking at the different properties, the different responses. And you can see if we look at just the hardness response from our different elements, we have quite a good significance of p-value, but also quite a high f-value. This f-value is basically showing that the higher the number, the less chance that the model is being affected or could be just considered as background noise. So we want quite a high number here, which is what we have, which is excellent. And we have a relatively low p-value. We typically say a p-value less than 0.05 is significant, and something above 0.1 is not significant. So you can see all of our input factors here could be considered significant. And that's quite good to know for our hardness model. And it means when we plot our predicted and actual, we actually got a very, very nice fit between our predicted hardness and the actual measured hardness, meaning that we can create some surfaces and quite accurately understand and predict the hardness when we start changing these variables, increasing or decreasing them independently. From the ANOVA analysis, we also got this linear regression model for an equation for our overall hardness, which should give us pretty good statistical accuracy for any sort of changes we make in our future alloy design for this. What I was particularly interested though is try to fit an ANOVA analysis to the yield strength, because this is a bit more complex, I would say. We have a lot more interaction in terms of dislocation movement, and then it's not just solid solution hardening or strain effects, but also electron structures and a lot of complex things going on, which are very difficult to model empirically. So we looked at first a simple linear regression model, and you can see pretty quickly a very low f value and a pretty high p-value. And that shows that our overall model is just not significant, and even the individual terms are far from significant. So instead of using a linear model, what I did was using a Poisson regression, which is looking at the change in the log terms of the individual elements. And we found that we got an overall p-value of 0.01, which is not as good as our hardness model, of course, but it's still what we will call significant. It's still less than 0.05. And looking at the actual individual elements within our model, you can see that at least for copper and magnesium, we could still consider this a significant result to the model. Zinc is starting to increase a little bit. 0.1 is typically the limit, we would say, for anything above 0.1 is not significant, so it's not as reliable. And then our silver factor is not so significant in this model. But if we still look at the model that we can obtain from this Poisson's regression, you can see on the right-hand side the values for the predicted yield strength, and on the bottom the actual yield strength. And you can see the model is not too bad. With a little bit extra data, which I have produced another 4 alloys, and the plan is to produce a few more alloys, we should hopefully be able to increase the significance of this model. And so far, the inclination we have is that we do have a few interactions specifically between the silver and the zinc, but we don't have enough data yet to actually include higher order interactions into our model without making it totally insignificant. So we're still increasing a bit of, so I'll come to the question shortly. We still need a slightly more data to be able to increase the fit of the model, but it's a very good base for us to start our next development of alloys to try to increase the yield strength without sacrificing the elongation where we can. I'll pop up the actual equation here for the Poisson's regression, but it shows we do have a much higher effect from the copper and the magnesium than we do from zinc and silver. And this is something that we expected just from our fundamental solid solution hardening empirical equations, where we have a much bigger misfit with copper and magnesium than we do with zinc and silver. So basically the future outlook for this work is that we can quite clearly see from the analysis that magnesium is the most potent element in terms of hardening and yield strength, but we do sacrifice a bit of the ductility with this, with zinc and silver actually helping a little bit with ductility without changing the yield strength significantly. So we're using this to redesign a number of our alloys in the next iteration so that we can try to maximize the mechanical properties within these aluminium cast alloys. I've got one question here I'll take quickly. Do you consider the lack of fit for your models? You may have to, sorry, I went too far forward then. I may have to just add on the question a little bit. Do you mean in terms of the p-value being slightly too high? Where did my chat? Yes, of course, we're trying to optimize the p-value to be as low as possible. I did play around a fair bit with, similar to what Jakob have done, with leaving out parameters, but I didn't get such a good overall model because we do still have some interaction with silver. I do want to improve the models with, as I said, more data, but changing compositions significant, like a lot of times, is a lot of work, which is why we need to be a little bit clever with the number of alloys we choose to produce. Otherwise, if there's any questions, please feel free to ask. Otherwise, thank you so much for your attention, and I'm looking forward to an interesting panel discussion at the end of this.
Okay, so thank you very much, Patrick, and also thank you very much, Jakob, for these nice presentations. And as we always want in these webinars is to have a good discussion after the presentations, because probably that's where the interesting questions comes up and you can really focus on your interest as an audience. So with those words, I would like to invite you all to continue the discussion. So Jakob, over to you.
Yeah, as Madeleine said, we're now opening up for discussions, so feel free to raise your hands in the